What is your name? How do other people call you? Today, let's talk about that. Hi guys, welcome back to our channel. Today's story is about names. Names like your name. How did you get a name? You have a name to identify yourself from the rest of the group. What if you were not given with a name? Then there won't be a way to identify you separately. Likewise, atoms are given with names. Why? To separately identify them. How do we name atoms? We name atoms from the number of protons in the nucleus of the atom. The atom with 6 protons is called carbon. The atom with 14 protons is called silicon. The one with 28 is nickel. So and so. Jeffrey Moseley identified that atoms of each element have a characteristic number of protons. Like atoms of hydrogen have only a single proton in its nucleus. Moseley called the number of protons in an atom of any element as its atomic number. Atomic number, the identity of an atom, is basically the number of protons in an atom. Atoms are neutral bodies. Remember, we discussed the neutrality of the atom from Thomson's plum pudding model in our very first video. Since atoms are neutral, the number of protons should be equal to the number of electrons. Positive equals negative. So in an atom, the number of protons should be equal to the number of electrons. The atomic number, number of protons, number of neutrons should be the same numerical value for any neutral atom. Scientists identified another figure which can be used to describe the atom. It is the mass number. Mass number is an indication about the nucleus. It gives the total number of protons and neutrons in an atom of the nucleus. For the unknown atom X, proton number or the atomic number is denoted in top left corner, and the mass number, the number of protons and neutrons together, is given in the bottom left corner. Here, the atomic number is given in Z and the mass number is given in A. Let's get this from an example. What is the number of protons, electrons and neutrons of an atom of palladium? Top left is 46. 46 gives the atomic number. Bottom left is 106 and that gives the mass number. If the atomic number is 46, number of protons should be the same. Palladium atom is neutral. Therefore, the number of protons should be the same as number of electrons. Mass number is 106. That is the total number of protons and neutrons together. Subtraction of the number of protons from the mass number gives the number of neutrons. Story of the mass number changed with the discovery of the mass spectrometer. J.J. Thomson with William Aston perfected the mass spectrometer. Here, once the unknown sample enters, it vaporizes. Next, gaseous sample is hit with electrons to make ions out of it. Ionized gaseous sample is accelerated in the electric field. Up to the state everything happens smoothly. Next, During the magnetic field, Thomson and Aston observed a deflection of the ions. This deflection was different for different ions of the same element. Deflection varies as a result of the mass of the ion, but it is the ions of the same element. Electrons only lost during the ionization, and mass of the electron never causes a change in atom's mass. Mass of the atom is all about the mass of protons and neutrons. If it is the same element, mass of protons is the same. It is the identity of the element. Sherlock Holmes method. Once removed all the improbable, what's remained is the most probable. What we have done in this experiment was just ionization, removal of electrons. That doesn't make any changes in the nucleus. Neutrons. Atoms of an element is originally with different neutron numbers, even though the proton number is the same. Atoms with the same number of protons but different number of neutrons is called isotopes. In an isotope, it is the identical atomic number but different mass number. Isotopes may contain similar number of neutrons as protons, or higher or lesser. Depending on the number of neutrons, stability of the nucleus varies. So isotopes could be stable or not stable. We call these non-stable isotopes as radioisotopes, which undergo radioactive reactions. Up until now, we talked about the mass of the nucleus, mass of the atom. How do we measure the mass of the atom? What can be the unit? Here comes the smallest unit in mass scale. Unified atomic mass unit. This is given in simple U or Daltons. We can define units. You can search the definition of gram, kilogram, ton, anything, just Google it. How can we define the atomic mass unit? Instead of just defining, we do a little trick here. We say it is the mass of exactly 1/12 of a chemically unbound atom of carbon-12 isotope. To find the mass of carbon-12 isotope, we divide the mass number of carbon by Avogadro number. Why? Because 12 is the mass of a mole of carbon. And 1/12 of that is equal to a 1 unified atomic mass unit. We learned that due to the presence of isotopes, naturally occurring elements exist as a mixture of isotopes. Carbon exists in a mixture of 3 isotopes. Then what is the mass of carbon? Imagine you have a classroom. What is the weight of students? There may be students with various weights. In order to get a general idea, we get the average of weights and state the average weight as a weight of a student. Same scenario. Mass of carbon is the average mass of its isotopes. When we calculate the average weight of a student, we add all the weights together and divide it by the number of students. Here, we add the masses of all isotopes together and divide that by the total number of isotopes. In other words, isotope mass is multiplied by the fractional isotope abundance. There is another physical quantity we have to deal with when talking about mass. Relative atomic mass. Mass of an atom relative to what? relative to the 1/12 of carbon-12 isotope, or relative to the unified atomic mass unit. In the periodic table, what they have given under the symbol of the atom is the relative atomic mass. Mass, atomic mass, mass of the nucleus. Atomic mass is due to the mass of the nucleus, mass of the protons and neutrons. Mass of electron is negligible compared to the mass of proton and neutron. In an atom, protons and neutrons are located in the nucleus. What about electrons? Electrons are located in orbitals. Orbitals indicate the electron's probable location in energy levels. We are talking about three major types of orbitals. First is the s orbital. Here, the electron density is spherically symmetric around the nucleus of the atom, which means the probability of finding electrons in this orbital is spherical. As the energy level increases, s orbital gets larger. Not all electrons inhabit s orbitals. There are orbitals called p orbitals in addition to s orbitals. P orbitals are dumbbell in shape. It points in a particular direction. At any energy level, we have three p orbitals directing at three directions x, y and z. Therefore, these are given the symbols px, py and pz. All energy levels except the first energy level have p orbitals. In addition to s and p orbitals, there are some orbitals available to electrons at higher energy levels. At the third level and upwards, there are 5 d orbitals in addition to s and p orbitals. D orbitals come from various shapes and they have named as they oriented in 3D space. dxy orbital lies in the plane of xy. dxz orbital lies in the plane of xz. dyz orbital is in the plane of yz. Each orbital has 4 lobes and each lobe is pointing between the two axes on the plane. Complications arise with the next two orbitals. dx squared minus y squared orbital has its lobes along the x and y axis. dc squared looks like p orbital wearing a donut around its waist. This lies along the axis of c. Even in the same energy level, d orbitals are in a higher energy state than s and p orbitals. We will learn these in a later slide. In addition to s, p and d orbitals, we have another set of orbitals as f orbitals. Now, we know most about the atom. What it consists of, where protons and neutrons are located, where electrons are, how their movements are. So let's dig deeper into the location of electrons. Niels Bohr introduced the concept of energy levels. He described the single quantum number n to explain how electrons are located in energy levels or in orbits traveling around the nucleus. This is the principal quantum number. This is the main energy level or the shell that electrons occupied in an atom. As simple n increases, orbit becomes larger in size, that electron movement spreads across a wide area and they have to spend lesser time near the nucleus. Next, the angular momentum quantum number. defines the shape of orbitals in an energy level. We discussed three main types of orbitals, S, P and D, short while ago. These orbitals are represented by angular momentum quantum number, and it gives the number of possible orbitals in a shell. Set of orbitals with the same principal quantum number and the angular momentum quantum number is called a subshell. Each subshell is designated by a number and a letter. For example, 2p orbitals are in the 2p subshell, 3d orbitals are in the 3d subshell. Magnetic quantum number describes the orientation of orbitals in space. In each orbital, maximum 2 electrons are allowed. Spin quantum number. Two possible values that are permitted to the electron spin. Once the electron spins, spinning charge creates a magnetic field. When the electrons spinning are in opposite directions, each magnetic field cancels out. Let's see how we can build a relationship between the principal quantum number symbol n, angular momentum quantum number symbol L, and the magnetic quantum number symbol ml. Energy level can start with 1. For the n equals 1 stage, L can be from 0 to n minus 1, which is 0. So when n equals 1, L can only be 0. The 0th orbital is designated as the s orbital. This is the 1s subshell. ml could be from minus L to plus L, which again becomes 0. For the 1s subshell, there is only a single orbital possible, which makes that single orbital is the only orbital contained in the first energy level. In that single subshell of 1s, 2 electrons can be occupied with opposite spins. Next, the case where n equals 2. Then, L can be from 0 to 2 minus 1, which is 1. There are two types of orbitals in the second energy level, 0 and 1. Orbital denoted as 0 is the s orbital, and we saw that earlier. 1 is the p orbital. For the 0 orbital or the s orbital, ml could be 0 as the previous one. That is the 2s subshell. For the 1 orbital, ml could be minus 1, 0 and plus 1. So basically, p orbital contains 3 subshells as 2px, 2py and 2pz. Altogether, there are 3 p orbitals and 1 s orbital in the second energy level. So to sum it up, 4 orbitals are there in the second energy level. Let's try the third energy level together. When n equals 3, L could be 0, 1 and 2. 0 similar to the previous case, 3s subshell. 1 similar to the previous case, 3p subshell. 2 is the d orbitals. 3d subshell. 3d subshell contains 5 different orientations as minus 2, minus 1, 0, 1 and plus 2. Totally 5 plus 3 plus 1, 9 orbitals are possible for the third energy level. You can try out the fourth energy level as a homework and check the answers later. Now, we are almost familiar with the positioning of electrons in the atom. We know where energy levels are. We know where orbital subshells are. Now, we are going to place electrons in the atom. When electrons fill into the subshell, it follows a particular order. This order is based on energy. Filling of electrons begin with the subshell of the lowest energy and continues upwards. This is given in Aufbau principle. Let's write down the subshell in each energy level first, and then let's draw diagonal arrows connecting subshells together. The path of arrows give the order of electron fill. Keep in mind that each subshell can hold maximum 2 electrons. Electron fill as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2 likewise. Wolfgang Pauli stated that no two electrons can have the same set of quantum numbers. Two electrons can share a single orbital. For an orbital, N, L and Ml values are the same. So for the electron in that orbital. In order to have a different set of quantum numbers to the second electron, Ms value should be different. Therefore, the second electron should have an opposite spin. In another rule, Hund's rule states that for degenerate orbitals, that is the orbitals with the same energy, stability is achieved. In other words, lowest energy is occupied when the electrons having the same spin is maximized. When an electron fills into the px orbital, the next electron won't come to the same px orbital. Because if it comes to the same orbital, spin should be opposite according to Pauli's rule. Hence, the electron goes to the py orbital and have the same spin. Next electron goes to the py orbital with the same spin. Electrons occupy orbitals singly to the maximum possible extent before pairing with an electron with the different spin. With the fourth electron, Pauli's principle applies. This is the same for d orbitals as well. Let's have our favorite question session now. What can be the electronic configuration of magnesium? Atomic number is given on the top left corner of the atomic symbol. We now know that atomic number equals to the electron number in an atom. So there are 12 electrons need to be filled into orbitals. You can of course go back and refer to the diagram we talked about in Aufbau principle. And let's start with 1s2, 2 gone, 2s2, 4 gone, 2p6, 10 gone, 3s2, 12. Now the outermost energy level electronic configuration. Our outermost energy level in magnesium is the third energy level. Third energy level contains only a 3s subshell with electrons. It is 3s2, which means the orbital is completely filled with electrons. 2 electrons are there. So the first one comes. Second electron comes according to the Pauli exclusion principle with the opposite spin. Selenium with 34 electrons. Shall we try it together? 1s2, 2 gone, 2s2, 4 gone, 2p6, 10 gone, 3s2, 12 gone, 3p6, 18 gone, 4s2, 20 gone, 3d10, 30 gone, and 4p4. What is the outermost energy level here? Fourth energy level, and the fourth energy level contains 4s and 4p subshells with electrons. 4s subshell is completely filled with 2 electrons. 4p4, only 4 electrons have filled. First electron comes, second electron comes to the next orbital according to Hund's rule, maximizing the electronic spin. Third electron comes to the third orbital, and now the fourth electron. It has no more unfilled orbitals, so the electron will have to go to one of the 3 orbitals with the opposite spin. Now you can try for chromium. What is it? It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4. This is the outermost electronic configuration. Does it seem okay to you? Hund's rule again. Electrons fill the way it maximizes the electron spin. One d orbital is empty here, and the s orbital is completely filled. If we can get one of the 4s electrons to the empty 3d orbital, we get 6 unpaired electrons with the same spin, maximizing the electron spin. So for the configuration, it rearranges as to this. You can try these with elements like copper, molybdenum, palladium. Let us know your work. Share with us on ilearn.sled@gmail.com. Let's wrap up today's work. We talked about atomic number, mass number, isotopes, orbitals, quantum numbers, electron configurations. Hope you had a nice time with us. Let's meet again with another cool lesson. If you haven't subscribed us yet, subscribe us to show some love. Have a nice day, guys.